Okay. Good afternoon, everyone. My name is Conio Cando. I am Project Officer at Erohipan Power, and I would like to welcome you today to this webinar from digital twins to decarbonization, lesson learned from the Green Heat Life project. We will have two sessions. The first session is about the decarbonization and district heating network transformation with digital twins. Our speakers are Evelyn Chen, Solution Lead from Gradient, Steen Jensen, Director of Business Development from Gradient. Then we will have a small break of 10 minutes, and we'll start with the second session, Green Heat Life Scenarios for the Future of Sustainable District Heating. We will have two speakers, Roy Askam, Asset Manager from Enator League, Jan Stock, Project Engineer, District Heating Network from E.ON. And then we will have some time for some questions after each session, and we will have some final closing remarks. Thank you everyone for joining. So I call Evelyn, our first speaker.
Yeah. I think we have 10 minutes. That was fast.
Yes.
Right. So put this here. So good. Yeah. So good afternoon, everyone. Welcome all to this workshop hosted by European Power and also Green Heat Life program. My name is Evelyn Chen. I am a solutions lead from Gradient BV, and I'm also the program coordinator of Green Heat Life program. So if you're actually familiar with the life subsidy, I think this title might seem a bit cliche, as all the life program are about decarbonization of district heating network and facilitating investment plan for network transformation. So for today, I'm trying to put like my 2 cents here on how like our program has a unique, let's say, concept and our plan to make a replicable decarbonization pathway for district heating networks in general. Let me bring you to the next slide to get started. I think before we start, I would like to show you a few pictures of like some famous engineering failures in the last century, actually. I'm not sure if any one of you recognize this one, which is, I think, was a department store in South Korea. And this one is it's loading a bit slowly. Yeah, it's a Haya Regency, like a pathway fell and back in the States. And one more, there is a that's the what was this one again? Sorry. Yeah, it's the Hartford City Center roof collapsed after a big a storm of snow in 1977. So so if you see this big engineering failures that probably killed a bunch of people, what was the first impression that you think? It's a big engineering failure, but they say the key point here is that when the key scenarios are not modeled or simulated ahead of time, the result can be quite catastrophic. So you have a major cost overrun, you can have like a major failure in your building or your construction program, or even loss of life. So just for information, the 3 accidents above, together killed about 500 people and left a few hundred injured. So this is what exactly advanced digital simulation helps prevent, by testing the what-if scenarios before any decisions are locked in. And this is also what we bring in from Green Heat Life program, where we focus on advanced digital modeling of the transformation process of your district heating network systems. We want to help district heating operators and your organization to build robust scenario simulation in the early phase of planning, where you can reduce risk, save money, and improve outcomes. Let me go to the next slide. So I'm not saying that we might cause life-threatening events with district heating transformation, but we all want the change that we invest millions in for like to bring positive outcomes, and we do want to keep people's home warm while like decarbonizing the networks. So let's say if the money goes in, and then we don't know how like how the result is gonna be, and then you might end it up in like on the good side or on the bad side. So hopefully we all have the outcome from the right side where your heat supply safety is insured and then your network is running at optimized operational cost and the investment is worth itself. So to make sure that we go to the right side instead of the left, while facing a lot of uncertainty like your energy price volatility, policy pressure, CapEx risk, and other uncertainty with the investment. With Green Heat Life, we try to design a replicable and foreseeable pathway using digital twin as the core. How do we do this? Let me try to run you through. But before, I want to give a bit like a set of the stage for the program today. So yeah, in the first 15 minutes, that's including just the time that we spent now. I will try to run you through the program information. So like what actually enabled us to do this kind of experiment, and who we are, and the program concept, where we talk about how we actually help district heating network system with the decarbonization process with digital twin. Then the presentation will be followed by Steen Jensen, who is my colleague, and some of you might already know him as well. He will spend about 20 to 25 minutes talking about the digital twin technology, which is kind of like the core that we use for this program, and how it brings values and future-proof solution apart from just doing scenarios with our program. And we will leave 10 minutes for Q&A. Followed by the Q&A, we will have a 10 minutes break for everyone to refresh themselves. Then after that, we will have two presenters from the consortium of the program to present their current progress, learnings, and achievements. Each of the presentation from the partner will be 15 minutes and also followed by a 5 minutes Q&A. In the interest of time, I will just go to the next slide and get started. So this is what to set the ground. What enabled us to draft this and experiment this concept from Green that we kind of propose is we have this program we apply for a life program subsidy that is funded by European Commission, where we're under the subcategory of clean energy transition. This program lasts for 36 months, and we started back in October 2024. So now we're almost at the middle of the program, and we plan to wrap up in September 2027. That's next year. We get a contribution from the European Commission for about 1.74 million euros, where we have 7 partners across 6 countries, where also we have 7 district heating network involved to testing out this concept that we have. So speaking about the consortium, so that's where who we are. First of all, we have Radian, who is the technology provider for digital twin, and we have Euro Heat and Power as our communication and dissemination partner. Then we have 5 district heating operators involved, where we have SAE from Mantova, Italy, and we have Klaipėda Energy from Lithuania. We have Aeon from Germany and Anatulik from the Netherlands, and they're also the 2 companies that will be sharing their experience in the second session. And we have Umeå Energy, which is actually the cause of our meeting today physically, and we're mostly sitting in the same room here. We have 7 district heating systems that are involved in this program, 3 from Germany, and then 1 from Italy, 1 from Lithuania, 1 from the Netherlands, and also 1 from Sweden. So before kind of like moving to the kind of the concept and the methodology of Green Heat Lab program, I would like to stress a bit on the program focus. So there are various live programs out there, and then each of them have different focuses. Like some of them would focus on capacity building or policy advisory, or technical demonstration like testing some advanced new hardware technology in different sites. From, let's say, kind of different from all of that, our focus is digital optimization and modeling, where we try to focus on like modeling the district heating system networks. We create like what we call a virtual replica of the network, built on combining historical operational data and physics modeling. That's what we use as a base for to simulate the network behavior in different scenarios, where we also use that for a bunch of different purposes, like forecasting the demand, balancing supply and demand, identifying bottlenecks, and finding solutions for peak shaving. With this property, we're building the digital twin for our partner networks, using it as a base for our investment scenarios. What is unique about this solution is that apart from doing static and offline scenarios, we can simulate the whole operational condition and are able to show the, let's say, expected operational condition in a comprehensive application interfaces, which I'm not gonna actually say too much now because I will leave that to Sting to talk more about it. So the let's say like one sentence to kind of like summarize is, before you spend 10 to 30 million euros, you want to simulate it first. And that gives you more confidence and clarity on what's going to happen after if you spend this much money. And then the program concept and methodology is about how we start and then how we plan to move forward. Of course, like the first starting point is that you would need a district heating system and your ambition to decarbonize it. Then we need some, let's say, basic demand and asset data that you can collect from your network and your system. Then we build a digital twin foundation where we model the full system with the validated historical data. After we build the digital twin, then it comes the scenario-based planning, where with the plan of the district heating operator and also some discussion between parties, we will set different scenarios like testing out different source and technologies, like switching fuels or like adding renewable sources to the network. And we also look at the cost and CO2 trade-off in terms of these scenarios and trying to manage the risk and uncertainties. With the outcome of the scenario study, each partner will develop tailored investment plan according to the outcome of the scenario studies. And also we help with exploring different funding options for the investment that they choose, and trying to plan a, let's say, reasonable timeline and alignment on stakeholders and other relevant topics. So at the end, of course, we want to have, let's say, a measurable or measured impact on CO2 reduction and also primary energy saving. And we would like to also have, let's say, optimize the system for operation for the partner networks. And we also have the ambition to replicate this concept in 15 networks within 5 years to drive a long-term impact. That brings me to my next slide, talking about the expected outcomes or impact. In terms of money-wise, we expect to trigger 158 million euros in capex. We also wanted to increase somehow the efficiency of the network using renewables, and then try for them to integrate renewables in the network, saving also 5 to 10% of their OPEX, with the hope to have ultimate impact of 85,000 megawatts hour a year in primary energy saving, 5,500 tons of CO2 per year saving. That's roughly equal to 3,000 like a European household, or could be like a very small town. And yeah, then we have an overall ambition to set up, let's say, as much as possible, like digital twins for like network across Europe. We also wanted to set new standard for district heating system to optimize energy use and boosting sustainability energy share. And also there is a part of the program where we want to provide recommendations to the EU policy, where we can help drive the change and facilitate decarbonization of district heating networks across Europe. That is all from my side, I think. So I will give the stage to Steen for him to share more about, let's say, how digital twin work and real cases.
Yes, thank you, Evelyn, and nice to meet you all. My name is Steen Schelle Jensen. I'm the business development director of Gradient, and besides this, I'm also active in the Euro Heat and Power digitalization working group, and also represent Euro Heat and Power in the Smart Energy Expert Group in Brussels. So working a lot with the digitalization, of course, and today I'll be happy to bring a little bit deeper into to the digital twin technology, and not at least why and what we're actually solving with the technology. I think if you look at the district heating top down, I think that there are three major drivers. I think we can easily say that all district heating companies are somehow in some sort of transformation during this year, and like Evelyn just said, then of course decarbonization is a super important topic, together with expanding district heating networks or building new district heating networks. We need to decarbonize the existing systems, but we also need them to expand them to grow the district heating footprint of Europe. I think there's been a lot of studies also from the Heat Roadmap Europe program, how much district heating is actually feasible in Europe, and it's a lot, right? So this is certainly a driver. And while decarbonizing while expanding, then we still need to keep costs in control, and we need to keep heat prices low. District heating still needs to be affordable to succeed compared with competing technologies. And then as the last point, I will mention that district heating is moving from being, heating only to actually also being a part of the wider energy system. We see that in some countries already, but it will just grow and grow. That other sectors will need district heating, for instance, to balance the electricity market, or you can combine with other sectors to pick up waste heat and so on. So again, district heating is no longer about its own operations or setup only, but district heating is becoming a market actor in the wider system. And I think all that drives that we go from this situation where we have systems with relative few heat sources, central heat sources, relative high temperatures, into systems that are more decentral, built with multiple different heat sources, again integrated with the industry, electricity, maybe combined heating and cooling. Again, examples that we are actually transforming. And now I'm located in Denmark, so just 3 quick examples on how could that transformation look like in Denmark, and then we will hear some other examples later today from this program. But this example here, maybe you already heard about it, on the west coast of Denmark. where they're replacing going directly from coal CHP to the world's largest seawater heat pump, 50 or 60 megawatts in the city of Esbjerg. And again, with all the combination of e-boilers, the heat pump, biomass, etc., to replace the coal. And this is not just on paper. This has actually gone live and is working well and as expected. Another situation or example here where this company, they had a big gas-fired CSP and they want to decarbonize and change, and they are building a variety of sources around here, building the world's largest solar thermal, and adding up with air source heat pump, biomass, putting in large accumulators at different temperature levels, putting in big e-boilers to simply make this heat production fully renewable. And last example here, also one of the biggest cities in Denmark, where they operate the last coal-fired plant in Denmark that has to be shut down in 28, taking away 50% or more of the heat, and they have to find out and substitute with alternatives here. Trying to establish this heat plan for the future, to put in waste heat and whatever heat source they can find. They are building, like you can see to the picture on the right here, big buffers to create flexibility in the system. Just some quick examples that this transformation is going on, and countries are different. It happens at different pace in different countries, but it is certainly happening. And I think along with this transformation, we need digitalization, and the need for digital tools is being increasingly recognized. And the reason for needing it is, of course, that this triple challenge or these strategic drivers, they kind of forces complexity and speed and uncertainty. There's a lot of potential outcomes of the transformation, and it requires somehow an understanding of many different possibilities to kind of evaluate and discuss before you place your bets. So like we also discussed today, that will require that you can test, make better investment decisions to make sure that, again, you place the right bets, of enable you to do these scenario-based planning is super important, and you will need tools to do that. And then once the systems are built, these super complex decentral systems, then you will need some kind of continuous optimization to actually improve the operation of these systems, and really like enable you to be proactive from a system operation point of view. And if we look at traditional tooling, then great things has been done in district heating over the years. Many companies are super efficient on operating district heating systems, but with the transformation, we have this complexity coming up, and I mean, some of the existing tools are simply no longer feasible for the new reality, and we cannot rely no longer on looking into the different silos of the systems and doing sub-optimization. We need to optimize systems in a whole from the end to end of the value chain. We need models that are not static models, but we need data-driven, accurate models to do, again, this continuous optimization. So not that the industry has not done good, there's just a need for doing even better in a more complex world. And this is exactly why we do the digital twin technology, and this was why Gradient was founded 6-7 years back. We are right now 140 people working in data science, working in energy, together with many of the largest European district heating companies to enable this future. And this is what we will dig a little bit more into And again, just to illustrate complexity, like we are moving from this traditional world where you have maybe one central CHP plant, you produce heat, you sell electricity, and of course you have to plan that every day, fairly simple, fairly stable. What happens then is you can of course improve and optimize on the heat demand, then as systems grow, becoming more decentral, maybe you introduce heat pumps, then you suddenly have to deal with not only selling electricity from your CHP plant, you always also have to buy electricity for a heat pump. Maybe you have direct lines and you can prioritize your own electricity consumption before selling to the grid. When you introduce heat pumps, then it's also natural to put in storages, and again adding complexity to the operation, because now you need to consider when to run your assets and how to utilize your buffers or your accumulators best possible. At the same time, many of these new assets like heat pumps are very temperature sensitive. So when you do your operation, you also need to take care and lower the temperatures for the heat assets to become more efficient. Sorry, I just have to. At the same time, we see that markets are becoming more volatile. Right now, electricity market has moved to 15-minute values. So simply, just an example to kind of tell that that complexity is really increasing in the operation. And to deal with that, we believe from Gradient side that every system needs or deserves a digital twin, because when we have a digital copy of the physical reality, when we can model the entire system from end to end, then we can first of all optimize the daily operation. We can do the different design studies and scenarios we are doing in this program here. So simply makes it quite much easier to deal with the increasing complexity. And what we do with the digital twins is basically to gather all the data that are there. It's not a matter of installing a lot of new sensors and data points. In most systems, we have data available, so you can consider this digital twin a smart layer on top of all the existing systems and silos. So we connect data from SCADA, from substations, from pump stations, whatever, in the systems, from the smart heat meters. And then we use all that information to calculate and model the system. And I think when we do that, and it can be important to note that the term digital twin is being used quite often and in many different situations. But what we as Gradient mean with the digital twin is I would focus on 3 points. First of all, what we can do is that we can build a real-time twin and make the digital twin live. So, for instance, in terms of the continuous optimization of the daily operations, then it's not enough to tell what you could have done and should have done yesterday. It's about giving you advice and telling you what is actually needed right now. And the other important point about the twin is that it should be end-to-end. I will come a little bit back to why, but things are becoming more integrated, more decentral heat sources. You have hydraulics in between, so you cannot no longer optimize your production without also validating if your optimization is actually hydraulic feasible. So end-to-end is super important, and then the self-learning part, that we cannot no longer rely on static models only. We do need models or systems that learn and adapt to the reality, adapts the real efficiencies of the different assets, continuously learns about how the heat travels throughout the pipes, etc. And so this is what we do with the twin. And when we have this digital twin in place, then we can do the real-time optimization, and we can do also the scenario part. So basically, you can say that the digital twin is kind of a two-in-one solution that enables you to do, again, both optimization and do these design studies. And I think we also believe that the Gradient platform is probably the only platform in the market that allows you to do that at the moment. So we build a platform. We enable you to do production optimization to optimize the network, and we can even go out and also optimize the use and the use of the flexibility in the buildings. But I think it's quite often that there is a very strong focus to production optimization and network optimization at the moment. And this is probably also where most of the value is. But just to give a few examples, what we do is that this is from the platform where we have a full physics model of the pipes. We can show live what happens with your supply temperature, your turn temperature, flow speeds, etc. You can see that in real time. You can also go back and play back what happened yesterday, the day before, and so on. And it gives you access to like get eyes on what happens underground. As a part of the optimization, something which is a typical use case and place to start will be to, once we know what happens in the system, once we know how the heat travels, once we know the heat demand and learn how that adapts to different situations, then we can start to do set points for the supply temperature. Again, we can take different boundaries and limitations and so on into consideration when we do it. But then we would typically do set points like you see here. The blue curve is a set point predicted by the digital twin. The dotted line here is how we suggest the set point some days ahead, and then you have the purple line here, which is the actual temperature. So here they follow actually quite closely. Sometimes clients use it, as a recommendation, and then they adjust the settings themselves. But in many cases, we also see that clients or district heating companies wants to go into kind of autopilot, where we just write the set points to the SCADA system, and then it runs more or less automatically. And when we do this optimization, of course, we take all kinds of variables into consideration. Weather, of course, when we predict the heat demand, the actual state of the system, and so on. One of the crucial points for this is for instance, in these new modern or complex systems with decentral sources, to understand exactly, like you can see in this picture here, what area is supplied by which source in the system. Of course, it's not like very strict boundaries between the areas, but you can see the area in green here is the area where the green source, in the middle is typically supplying. So when we know and understand how do the different sources, what areas of the system do they serve, that's one of the reasons that we can normally understand and go very low in temperature, and to serve the buildings with just how much heat or temperature they need. Again, very, very important point here. And when we do this, then we always see that, normally temperatures are controlled maybe by static control curves or some kind of control curves in the SCADA. You see an example here where the red dots are from the historic operation of the system, and then the blue dots are the set points and operations suggested by our digital twin. And I would say that we have not seen any system where we have not been able to go significantly below the historic operation. And actually, in this case here, it's probably one of the most optimized, or was one of the optimized Danish networks in terms of temperature. They was very low before, and even with that, we were able to go like 3-4 degrees lower because we can be more proactive to secure that the needed temperature is there. And of course, it gives savings on heat losses. It gives the opportunity to improve the COP of the heat pumps because we can lower both supply and return temperatures. And again, that goes across all our systems. An example here where we were actually able to lower 8-10 degrees. That's not unusual. And again, when we look across all our different systems we have in operation, this is the typical case. Of course, benefiting again the heat loss, but also benefiting the temperature sensitive heat sources like heat pumps. Another example where we see the digital twin provide a lot of value is in the production optimization. And this could be a typical, or is actually a quite typical example again from a Danish client, but small medium-sized city here. They have 2 sites. And as you can see, every site has different technologies, accumulators, one with straw, solar, and a heat pump, another one with wood chip and gas boilers, and also an accumulator. You have them placed at different locations. You have the network in between. So how do you operate these assets best possible and produce the heat as cheap as possible? I think it almost speaks for itself that it's super complicated if you have to do this by Excel sheets or manual thinking only. So for this specific case here, it's that part of the system was a 65 gigawatt network, so it's not the super big network. But when we run the optimization and we do the optimal dispatch of the heat assets, then compared to let's say a traditional operation, then we are actually able to save 10% on the heat production simply by running the heat pump more efficient, utilizing the accumulator as best possible. Make sure that you are down on a low level in the accumulators or buffers when electricity prices are low, and you can maximize the production with the heat pump. Make sure that we avoid heat pumps in the expensive periods and discharge the accumulators and so on and so on. So it's quite significant, and again at the same time we reduce temperatures, so creating quite many savings in this situation here. Here you can see in the middle the temperatures where we again managed to lower the temperatures quite significantly with the twin, taking in data from the system, taking in data from 2,500 smart meters in this system here. Then some will claim that, okay, when you start to lower temperatures, then you will run into problems with flow limits or bottlenecks in the system. But of course, this is also managed by the twin. You can see to the right in these flow rate diagrams that yes, of course, when we lower temperatures, the flow will increase, cost a little bit extra on the pumping. But we were still within the limits of the max flow rate, possible to find this optimal balance between lowering the temperature and increasing the flow. Again, with the understanding from the twin on what happens real time in the system. And again, back to the production, as you can see here, examples where when we have low electricity prices, the light blue areas here, Then we run the heat pump as much as possible. We load or charge the accumulator. When you have the high electricity prices, then we discharge the buffer. So it's again knowing all the different strike prices of the different heat assets and knowing where they are located in the network, knowing the heat demand, knowing the level of the accumulators will allow you to do this optimization, cutting down 10% of the heat production cost, which is significant and which allows the investments for the company to allows the investment in these new technologies. I will not go into this today, but there is another important aspect, of course, that when we do this production planning, then because district heating is now a market actor in the wider energy system, especially with the electrified assets, then there is a lot on translating this production plan to bits and to integrate that with the electricity market to know exactly how much flexibility do we have, how can we optimize the district heating operation towards opportunities in the different electricity market. I think this deserves a whole individual webinar to discuss that part. But just to let you know that this is also a super important part of what we can do with the Twin. So to end up, I think, all district heating systems, they deserve a digital twin because, again, complexity is increasing. The speed in which you need to take action and decision is, again, increasing. So you cannot rely on gut feelings and traditional tooling as we see it. And when it comes to the different elements of the system, then of course it's important to optimize the production, optimize pipes, distribution, and so on and so on. But I think end-to-end optimization is really the key here. And I would say that you can. I mean, I'm not a music expert here, but I mean, if you play in an orchestra, I'm sure that you need to take care of the individual violins or flutes or trumpets or whatever instrument somebody is playing. This is important, but you also need to consider them together. And I think if we translate this to district heating, then you can consider the digital twin as being this conductor that makes your district heating orchestra play in harmony. Yes, thank you. I think that was what I would wanted to bring to you this afternoon.
Yeah, then I think we have like some time still for questions if there are any. Connie, I'm not really sure how we see questions, or do we allow people
Please come in the chat here.
Okay, they're like Q&A.
There's one asking, do you also use sensors for real-time data, EDM temperature distributions or leakages in your digital twins? I think I answered that already, that with the twin we built on top of the existing data. And but just to mention again that we don't see a data problem. I think most companies have enough data already and also in sufficient quality, and we can work with data in whatever quality and interval there is. So I think lack of data is not a big issue as we see it.
Okay. Is there like what? This was answered? I think so.
Yeah, then there was another question also about let's see here, when we optimize, I guess you can all see the Q&A maybe, but when you, for instance, are running a heat pump and at 0 price hours could be great for dispatching. but not for overall lifetime value. So how do we, let's say, optimize across across the optimization here in now real time, and also taking the different investment maintenance and so on into consideration. And I think that's exactly what we can do with the Twin. Of course, we can optimize. We take in all different price signals from whatever sources. So yeah, prices for, of course, from the traders when we do the dispatching, but we can also take other things into consideration when doing the dispatch. I mean, it could be that you can only run this heat pump for X amount of hours per year, or if you start it, it has to run for a certain time before you turn it off again. You can maybe only ramp it at a certain rate. So yeah, we can take all these conditions into consideration as well. I just discussed with a client today where they had a contract of waste heat, and they had to take out the heat minimum 4,000 hours a year. And that's also a constraint you can put into the system. So it's not only technical constraints, it can also be, let's say, contractual or maintenance or investment related things or conditions. And then what the digital twin does is simply to take all that into consideration when doing the optimization. And that's, yeah, again, it's exactly the purpose of a digital twin, that you can do complex optimization across different targets or end goals, where you find kind of the optimum between different optimization targets. I hope that explains.
I think there's one more question.
Yeah, does the grader maintain separate database from data pulled from SCADA customer systems already existing, or use already existing sources? So we pull data from existing sources and use that to take use of that to train the model. Normally, when we onboard new clients, we get a dump of 1-2 years historical data to train the digital twin. This has also been done in some of the scenarios you will see later today. Then we take in live data to continuously retrain the twin. So we use both historic data, but also the live data coming in. But we integrate with all the different sources or data sources. Yeah. Feel free to ask questions also to Evelyn about the program if you have any questions on that.
No, these are answered.
Okay. So just if there is some questions that you would like to do, please raise your hand.
I think either typing in the quick Q&A or raise your hand. You can also ask a question live. I think we have a few minutes left.
Mm-hmm. And of course, here in the room, if there are some questions.
And you're also more than welcome to reach out to us. I mean, you can. I haven't shared my email address here, but you can ping me on LinkedIn, or you can. If you're in the room, you can catch Evelyn.
So on.
I see. Okay, if there is no any questions, so we can do the break. 10 minutes break, and we continue with session 2.
Okay.
Thank you, Steve.
Thank you.
Marietta, can I have a control of the slides, please, again? Thank you. So let's start with the second session. Welcome everyone. And we have now our speaker, Roy Scam from Renato League. Please, you can join us.
Yes, thank you, Connie. Welcome to the Green Heat Live scenarios for the future of sustainable district heating. I'm Roy Askam, the asset manager within Natuurlijk for the Enschede area. When you have questions, you can also send me an email. You see it on the screen. I have no control. Yeah, okay. First, something quick about Natuurlijk in general. What is leading us? Our mission in the Netherlands is working to more quickly achieve local and sustainable energy for everyone. Become the preferred supplier for delivering sustainable heat and cold. And our ambition is 70% CO2 reduction of our heat grids in 2030. And all our heat grids must be made CO2 neutral by 2040. Some numbers. We provide 58,000 customers with heat every day. We deliver 1,200 B2B, business-to-business customers, and you see on the map, we're located in the whole of Netherlands, where we supply more than 44 million gigajoule heat every year. Enschede area is in the east of the Netherlands, and we are the second biggest heating grid for Natuurlijk. Then to Enschede, you see here district heat network from Enschede. We have our heat from waste incineration and a bioenergy plant, not owned by us, so we buy our heat. We deliver more than 10,000 households, 150 business-to-business customers, over 450,000 gigajoule. There was a lot of developments in the recent years in Enschede. You see blue pipes and red pipes. We had in Enschede 4 decentralized heating networks connected to the large grid. The large grid is the blue one. So with a lot of expansion in Enschede. And what we also see is that the new grid is a big magnet for new customers, and also a great opportunity to make existing buildings more sustainable. Yeah. And then to the beginning of the project, some key focus areas and end goals. Temperature optimization in Enschede, reducing heat losses, lowering CO2 emissions, and accelerating the renewable heating adoption. And when to create a digital twin, you have to collect a lot of data and validate the data. And that's normally costs a lot of time. It's not only the production data or the delivering data, it's also flows, pressuring, set points, GIS data, control, physiology, and that on hourly or maybe on and maybe on quarter base in the future. Yeah. After the collection of the data, we begin to build a digital twin. And for Enschede, all the building work is done by Gradient. As you say, they're a specialist from building the digital twins. So, and in the end of the building period, improvements in temperature were already visible. And after some fine-tuning between Gradient and Natuurlijk, some scenarios for further decarbonization and improvements also emerge. So, and for Enschede, we had 3 possible scenarios that we will go investigate it further. So, there's the temperature optimizations. It's the heat pump at substations. Because in Enschede we have a primary network and a secondary network. And in the substations, we reduce in temperature and pressure. So the primary network is, we call it high temperature network. And the secondary network is the mid temperature network. Yeah. High is from 90 to 115. And mid is from, yeah, it can be all 40, 50 to 80, 90 max. Yeah. Now go further in detail. With the temperature optimization, we had in addition been 2 scenarios, a conservative scenario to reduce the forward temperature by 3 degrees, and an aggressive scenario where we reduce the forward temperature with 11 degrees. Yeah. So with the conservative reduce of temperature, we bring down the heat loss by 6%. So that's saving us fuel cost, and is also reduced in CO2 emissions. And for the aggressive, you see heat loss increased by more than 11% and reduce also more CO2 emissions. But in Enschede, we have to check the pump capacity on that. When we want an aggressive scenario, we need to place an additional transport pump. Yeah, yeah. And also, a thing is when you have too much transport capacity, you see the flow is maybe too high, then the return temperature is going higher, and that make the capacity of your total network. Maybe you have some problems there. And with the digital twin, we find the ideal set points, or we try to find the ideal set point for that. So, yeah, it's an ongoing process now. We can go to the next scenario. Heat pumps at substations. As you know, with a digital twin, you can identify also inefficiencies and bottlenecks. So to get more capacity from the existing network without investments in, by example, pipeline enforcements. This is a possible scenario we investigate. So with the heat pump at the substation, we use the return of the secondary of the primary network, and with the heat pump, we bring it up to 80 degrees again. So we use the return temperature, and we're lowering the primary return. temperature. So for the whole network, we think the capacity gets higher, and investments in pipeline enforcements can be later or is not necessary anymore. Yeah. Yeah, when you will significant increase in return temperature across the entire network, we see we have to make this scenario or more a substation is in Enschede. One substation is not enough. We have to make a start, but for big impact, we need to do more. Last scenario for now. We're very in the dependence on one supplier in Enschede. That's a risk. So we want some more control, and this is an option for that. So place 230 megawatt of electric boilers, and so reducing cost, and but we need a digital twin for that, also with the fluctuation of prices and that. Yeah, so we have to manage that. So the thought is when purchasing when a heat price is higher than the electric price, the heat boiler is designed to cover the network demand first and then charge the buffer. And on the other side, when the twins, our heat supplier now, when the twins price is lower than price, the buffer will be decharged if it's warmer than the return temperature. That's some technical, but okay. There are some challenges here because of the net congestion of the high voltage grid in the Netherlands. So there's some challenges of planning and implementations, and we're on talks with TenneT to make progress in that. Yeah, we need each other there. So we think we can help each other. So that's the status of the Green Need Life here for en natuurlijk at the moment.
Yes, so if there is any questions, please raise your hand, or you can write it in the question and answer box. And also here in the room, if there is any question, please don't.
And say you have like one supplier, it seems like you are just buying from one supplier and you're trying to kind of like decrease that dependency by becoming sort of like a provider yourself and so on. Right?
Yeah. Sustainable energy is 99% from Twents. Backup is in our own, but we don't need it normally. But it's a risk. Yeah.
I don't think we have questions online in the room. No. So we can move. Thank you.
Thank you.
Thank you. So yes, now we have Jan Stock from.
Yeah, thank you, Connie. Hello, also to the digital room. My name is Jan Stock. I am from the E.ON Energy Solutions GmbH. It's a sub-company of E.ON, and we are. Let me click one slide. Here we go. We are the sub-company in Germany providing heating and cooling solutions to the western part of Germany. We are operating around 50 district heating systems in the western part of Germany, with a total length of 700 kilometers grid length. And overall, we got heating and cooling capacities of around 1.1 gigawatt. So a lot of different systems with different sizes. And here in the Green Heat Life project, we analyze 3 of our 50 district heating systems. I have shown them here on this slide. These are 3 district heating networks, differs from each other in size, in customers provided. You see the map of Germany in the right corner, and you see that most of these systems are located in the middle of Germany, Dortmund-Schüren on the left-hand side, Marl in the middle, in the western part, and Schmalkalden in the heart of Germany, in Thuringia. I will focus on all of these 3 networks, but I will pick one scenario for each network. So in Dortmund-Schüren, our smallest network here in this project, we are focusing on integrating a heat pump combined with a thermal energy storage. So we focusing on decarbonizing the supply. In the middle, we have our largest network in Marl with nearly 100 kilometers of network length and a lot of consumers, over 3,000 supplied. There we will focus the scenario on supply temperature reduction, so making the distribution more efficient. And on the right-hand side in Schmalkalden, we actually have 2 networks, one in the city center, a little bit smaller, the left one, and one bigger network outside the city in an industrial area. There we are focusing the scenario analyzed with the digital twin of gradient by network expansion and network connection. So 3 networks and 3 different scenarios focusing here, and we get started with the first one, Dortmund-Schüren. As you see here in the overview, we are quite limited in expansion of the network. So we are focusing here on the supply and how we can decarbonize this supply. And we are planning to integrate a heat pump that will replace the current operating combined heat and power unit in 2035 to reach the renewable share of 30% in supply. So there we optimize with gradient how a heat pump can be integrated and operated in Dortmund-Schüren. And we optimized that there should be a heat pump with around 1 megawatt in heat supply. And this heat pump operates based on the electricity market. So we're buying at the day ahead market the electricity price and also doing operational optimization. So during times where the prices are low, we are operating the heat pump, and at high prices, the boilers will support the heat supply there. So therefore, we also want to integrate a thermal energy storage for load shifting. So we want to operate the heat pump at maximum load, so at 1 megawatt, for example. And if the demand is not as high as the nominal capacity of the heat pump, we can then charge the thermal energy storage. And some hours later, when the electricity price will rise up, we then shut off the heat pump, but we have the storage loaded, so we can discharge them and so operate the heat pump on the most electricity or most beneficial electricity price, but also at full load, so not in part load, which is not as efficient as the nominal load. So all in all, we showed that the heat pump can be operated for most of the year, despite we only have limited supply temperatures available. So the heat pump is only can only supply the heat at 70 degrees Celsius. And at lower outside temperatures, also the supply temperature we can reach by the heat pump will drop a little bit. So we have to mix up boiler heat. So the boiler will supply the heat. So we reach the high supply temperatures of the network around 90 to 100 degrees Celsius. However, all in all, the optimization showed us that we can reach with the heat pump here installed in combination with thermal energy storage a COP of 2.2 on average Of course, a little bit higher in summertime or spring and autumn, but a little bit lower in wintertime, around 1.6, but quite good on average for air-sourced water heat pump. The first analysis or evaluation of economic benefits showed us that we can save operational expenditures of 14% in contrast to not installing a heat pump. So installing the heat pump in the future will also have economic benefits and not only ecological, so not only reaching the renewable share we have to reach, but also from an economic point of view, it's very beneficial for us. So then coming to our next district heating system analyzed here, and also the next scenario, the district heating system of Marl. As I told you, one of our largest networks, 100 kilometer network length and 3,000 consumers supplied by the waste heat here. This comes from a chemical facility in the north of the city. And the digital twin showed us that we are operating the district heating system at very high temperatures. We know this, of course, but the digital twin showed us where we have these high temperatures, and we have it nearly in the entire network, so also in the outer pipes. And we know that the customers do not need these high temperatures, so they can also be supplied at lower temperatures below 100 degrees Celsius. And so we decided to focus here on temperature reduction. And you can see some results here from supply temperature reduction. And first of all, I want to highlight that, of course, for this optimization, we stick to two main points. First of all, the network, the pipes should handle the increased mass flows. As you know, when supply temperature reduces, we increase the volume flows. First point is that the network can handle the increased volume flows. And second point is that the customer supplied should, of course, always get enough heat supply from a flow point of view, but also from a temperature point of view. So keeping these points in mind, the digital twin showed us that we can decrease the temperature very much. You see this here, supply temperature reduction potential of up to 50 degrees Celsius during the coldest days. So on the right-hand side, we have the heating curves, similar to this, what Steen showed us before. We can decrease the supply temperatures very much during the coldest days, more than during the warmer days, but the potential is very high. In Marl, we can save up to 7% of distribution losses. And if you know, as you know, for 100 kilometer network length, 7% smaller network losses are a huge benefit for us for operational expenditures. As I told, the volume flows will increase. We also have an evaluation for the network here. So the digital twin showed us also where we have bottlenecks or where the critical points may arise with higher volume flows. You see that here in the east middle of the network, we have one pipe reaching 1.8 meter per second. It's still beneath the threshold of 2 meter per second, but we know this area of the network could be critical if we even further reduce the temperature or maybe add additional consumers to the eastern part of the network. And we also know which other areas might be critical for the decrease of supply temperature. So a very good experience we get here from the digital twin. One point to mention further is that we also experienced that the return temperatures of the substations are the most critical points. Of course, when we're reducing the return temperatures, we then also do not need to increase the volume flow as much. And we additionally identified most critical consumers that limit even further temperature reduction. So the results I showed you are reached or can be reached in the network. However, when we address 10 more critical consumers in the network, we can even further reduce the supply temperature. So there's still a high potential for further efficiency increase here. Coming up with our last district heating system and our last scenario, it's the district heating system of Schmalkalden. And as you see here, we have two networks, one in the city center on the left-hand side, and one bigger network in the eastern part where a lot of industry is currently. And with the digital twin, we are analyzing the expansion of the network as we can connect much more consumers in Schmalkalden, and also the connection between both networks. And we want to do this as both networks, when they expand, they come together in the city of Schmalkalden, but also we enable the network to operate much more flexible. So we are limited with renewable heat supply in the city center. So we want to install more capacity from or renewable capacity in the bigger network in the east. And so the outer network can also supply the renewable heat to the inner city network. And so we have a much more flexible operation here. So the analysis of the digital twin showed us that the connection is possible. We've expanded the network around or along the highest densities or heat demand densities around the city, and assumed a connection rate of 60%. And the digital twin showed us, okay, it's fine. You can expand the network. The current pipes can handle the increased volume flows, the increased supply, except these critical areas I've highlighted here. So there will be some critical areas for this huge network expansion. So in area 1, 2, and 5, we reached the limit, the threshold of flow velocity of 2.2 meter per second. So these pipes have to be replaced for such network expansion. However, it is quite limited. So no long network pipes need to be replaced. So it's still manageable. Furthermore, we know also that area 3 and 4 are not critical, are not at the limit yet. However, when we expand even further, or other measures like supply temperature reduction will be done in Schmalkalden, these area also might be critical and need to be replaced. With the digital twin, we also analyzed changing operation in the networks, and so, as you can imagine, also the hydraulic critical spot will move. So we will have another spot, and with the digital twin, we already know where we have to install new measures to measure the pressure difference in the network, and so have a reliable operation of the overall expanded network. Yeah, coming to the concluding slide, links and upcoming steps. So within the project Green Heat Live, we identified huge ecological and economic potential in all three networks, and identified really good measures for transformation and decarbonization. So with these three networks and scenarios I've showed you, we are focusing on supply, decarbonizing, for example, heat pump integration. We focused on distribution, so to increase the efficiency by temperature reduction. And we are focusing also on the consumers and identified that there is also huge potential when we handle the faults currently there in the substation of the consumers, and can reach very low return temperature there and have a big potential. What we also get to know in the project is that the exchange with the operational teams within the different district heating systems is very essential to build up a very reliable digital twin, but also to identify the most efficient measures with the operational team, as they have very good experience and knowledge about the systems, and it's crucial to get together all employees of this network. The upcoming steps are now that we have identified the most efficient measures in all three networks, and now we want to document it in an investment plan and a transformation plan. This is the next work package in Green Heat Live, and including funding mechanism and considering also the technical, financial, and regulatory aspects in Germany, we want to create then the roadmap and transform and decarbonize all of these three systems. So this is a small overview. If you have any question, please write, please contact us. We are very open for discussion and exchange. Thank you.
Thank you.
I think it's for me. I do not understand it. Is all this into most? What do you mean with all this? I'm a little bit confused.
Right? So maybe you ask this person to clarify a little bit.
Yeah.
Please, this question that is in the question and answer box, if you can clarify, you can open your micro, clarify your question.
So maybe like I interpreted there. Okay. Maybe I want to say a little bit to the first question how I interpreted it. So all these learnings, all these scenarios, temperature reduction are also transferred to our other district heating systems. So the learnings, of course, are documented in kind of blueprints, and we will also transfer them to the other district heating systems we are operating in Germany. So this is only the start, and this also will be integrated and transferred to other district heating systems as decarbonization and transformation. These aspects is also very valuable for the other systems. Maybe this is the direction of the question, hopefully. Otherwise, please write me. Second question.
Everybody can see the Q&A?
I think, no, so we need to read the question, I think. So we have a question. Did I see correctly in one of the early slides that the temperature,
I think you mentioned the MAL district heating system and the scenario of supply temperature reduction, and I showed there two heating curves. I might go back and with the slides. I think here you can see this window that in red we have the historic supply temperatures measured, and in dark blue or black we see the optimized supply temperatures. And I think the question was that here during the higher outside temperatures we have higher supply temperatures optimized by the digital twin. And yeah, this is correct, because the digital twin sees there that the return temperatures from an historic point of view is quite high in the network of MAR. So in summer, during high outside temperatures, we have quite high return temperatures in the network. And so the digital twin shows us we should also have quite or a little bit higher supply temperatures than historically. And therefore the volume flows in the network will decrease. And therefore we are saving some pump energy here. And this is then the optimized supply temperatures during high outside temperatures, recommended by the digital twin for optimal pump energy in the network and optimal operation there. So this is also to the return temperatures, which are quite high in MAL, and therefore we have the higher supply temperatures, and some are recommended.
Okay. Yeah, I think if you have answered the question, we should just move it down that you actually are more confused.
Yeah, maybe we can check if there are any other questions.
I think only these two questions here.
No.
There are a new question. Okay, thank you. So the reduced flow outweighed the higher temperature. Right. Yeah, this is the reason. The lower flows in summer are more beneficial for the pump operation, and therefore we are operating at quite or a little bit higher supply temperature in summer. Yeah, this is the reason. Yeah, of course.
Yeah, it was very interesting. Again, but the high end capacity when you're down in full so to speak, it's you can remove the chat box. Yeah, it's quite significant reduction on the twin there, and is it sustainable over time? So or does it need to? It's how I can't see the scale here, but it's a temperature on the
Yeah. The y-axis is the supply temperatures, and at around -5, yeah, we have only 100 degrees.
Okay, yeah. So I think it's a significant drop.
It is. So as the analysis here before, we've seen, okay, we have the high supply temperatures at most customers. They do not need 100 degrees Celsius. They can operate the heating system at 70, maybe 80 degrees Celsius.
But
So
do you have outlier customers that really you have had difficulties in supplying one? Do they all sort of comply with the?
I do not know from any critical temperature customer that needs such high temperature. Also, our operation team do not know from each one or any customer that needs higher or has some issues with too low temperature. So this is only from historic point of view that we're operating the heating system at such high temperature, very large. So you have from a historical point of view, very high supply temperatures. And so now we know at which extent we are too high.
But this is systematic for many of the grids in Germany. I mean, you can do this kind of optimization, many of the grids. It's similar or likewise.
Yeah, so we are planning it. Also, of course, each district heating system is individual, depending on pipe installed, customers, substations, direct, indirect. So it is very unique. However, we have potential in nearly each network, maybe not as high as here in Amal. However, a few degrees Celsius we can decrease nearly in each network.
Thank you.
And so we're saying like the set points are set, right? To well, include the like, do you plan to have a manually adjust according to it and manually adjust the temperature according to the set point? So do you just plan to have like sort of
I think we have an autopilot and a heat curve control.
Okay.
So depending on the outside temperature, we set the supply temperature. We do not have a live digital twin here, so we are taking the results here from gradient and discussing with our operation team how they change the heating curve at the plant. However, yeah, depending on the heating curve we showed here, so yeah, we are discussing at the moment.
So yes, there is no more question in the box. Is there any question that you would like to do? Please raise your hand in the room.
Otherwise, of course, please write Connie or us directly. happy for discussion.
Yeah.
Okay,
Okay.
then thank you very much.
Thank you. So yes, just to conclude our webinar today, I would like to ask you that you scan the QR code that you see in the slide in order to be informed what is happening within this project, Green Heat Life. This is the first webinar that we organize within this project, and we plan to organize more of them. And we also, this year, we plan to, if you visit our website and follow us in social media, you will be informed about the coming public reports about some results of the project this year. So thank you very much for joining us today. I wish you a good afternoon.